So what are we looking at here? So it's previous work. We should go over that a bit. Just look at what the yes. So this was the latest paper I did on the deriving the expansion rate of the universe and the Higgs mass and the vacuum expectation value and a number of other things. So we see we have this the cannonball problem, and that works into the expansion rate of the universe quite a bit. And yeah, so there's this idea of like the initial size of the universe. We have a, how do you say, it's like a proto hyperspace bubble. But so we have this maximum critical point at this value, and a minimum critical point as well at that value. So yeah, so when we look at this equation, we can turn it into a Diophantine equation of this sort, which is an elliptic curve. So then you can graph the expansion rate of the universe as like a continuous curve, as opposed to, you know, a kind of a discrete. This was the discrete scaling factor for the expansion rate of the universe. And then when we use the elliptic curve version, we get a smooth expansion rate. So that was the idea there. But then we're also dealing with elliptic curves, so we can, you know, get the modular form of that, which turns out to be related to SU2. So it's interesting. So there's the normal Weierstrass form of this equation, the elliptic curve. And obviously there's a lot of properties to the curve. So as you know yourself, and you can talk, you know, this is not a straightforward presentation in the sense we can, it's more of a conversation. But so within this, we have the elliptic curve I was talking about, and this is it in a different form. And then because an elliptic curve has is in a complex plane, we can. Oh, there's a little bit of feedback, Rajan. I don't know if you can hear that. If you can mute me, yeah. So that's a problem, though. So basically, when we have the elliptic curve, then of the rational field, that's better now.
Mute. Tell me when it's okay. It's better.
Yeah, no, that was good there actually. Yeah, you fixed it. Yeah, it's good. Yeah. Okay, so it has a basis. This is the basis of the elliptic curve, and so from this we can generate the lattice. Now, period lattices of this sort are used a lot in string theory. So if we look at some of Bayes' work, he goes into different aspects of string theory a lot, particularly bosonic string theory. And a lot of that is to do with basically you're looking at the ground state. So his equations here for, so, you know, he's got the cannonball problem, and they're linking that to the Lorentz lattice. Okay, so if we go through all of this, we got -1/12 and then so we're looking at the ground state energy. So -1/12 is the sum of all of the integers up to infinity, which is obviously related to, you know, quantum numbers, the frequencies of a harmonic oscillator. And so then this is where we get the idea of, because we have the infinite sum, which is -1/12, and then the ground state, which is, so we divide it by half, we get -1/24. But we want the ground state is more easily calculable when it's -1. So then you have to do like, what is it, a 2 plus n kind of calculation, which gives you 26 dimensions or 24.
I have one question.
Yeah.
The one before, you said 1 plus, how does it get minus 120, minus 1 over 24? 1 over 2,
Okay.
there's no
Yeah, that's
negative
curious.
sign.
It's Euler's equation, and Ramanujan was also involved at a certain point. But so Euler considered this function apparently.
Uh-huh.
So this is the Riemann zeta kind of function, 1 to the power of minus s, and so on and so forth. And when you do that, there's another way of looking at it as well. If you think of the Riemann zeta function, and you look at all the values of the Riemann zeta function above the 0 line, these are all easily calculable, but you can't go below. Actually, I think it's above 1, or well, certainly above 0 anyway. So as you go below, you need this thing called analytic continuation, because there's not actually any solutions down here for the Riemann zeta function. So you use this thing called analytic continuation, and then when you get to -1, I think it is, the value for that particular coordinate, so 0, like -1, 0 coordinate, is equal to -1/12, and it's also equal to the sum of all of the counting numbers. In terms of analytic continuation, the two are related. So that is, I think, the easiest way to explain that concept.
Yeah, but you should have the 1 plus 2 plus 3, it should be under the theta sign. It'd be the zeta of that, right? Because if you just add them, you are not going to get negative 1 over 12. You have to have the function.
I think there is a
It should
way.
be a function.
I think there is a way to do it. Ramanujan had a proof. Let me just see. I might have expressed that in a. See, the problem with this is that I think I spelled that wrong. I did. Problem with this is that it only searches the titles. So I would have to remember what the title of the just
You can search under your
way. Yeah, so there is a solution, but there's another way of looking at it where you take
when you put the equation like 1 plus 2 plus 3 plus 4 equal to negative, just look at the mathematics. It doesn't add up. What I mean is 1 plus 2. You have to put a function or something. You have to put a zeta of that is 1 now. That's okay, because there's a function that is doing the job. So you have to put that.
Yeah. Yes, possibly. There's a thing where Ramanujan does something. This will probably be a bit too complicated. Yeah, it is. So, this thing where you shift the values one space to the left. So you have an infinite series and another infinite series, and then you minus one from the other, and the two converge, and you get -1/12. And you can shift the series.
There should be a function,
series by 1 because they're both infinite. So
but when you equate that, the left-hand side should match the right-hand side. So if you add 1 plus 2 plus 3, it is some very large number.
Yes.
On the right side, it cannot be -1 or 2. So it has to be some kind of a function. It should be some time. The 1 plus 2 plus 3 plus 4 is inside of some function.
Well, I've explained it in two ways. One using the analytic continuation idea, which is a function based on Riemann zeta when it's because the analytic function goes below 1. And so there you go.
Yeah, that makes sense. Yeah, that's it. That's it. That makes sense.
You can also look at Ramanujan's proof when you get a chance. I think he does something along these lines, but I don't know if he
very
uses
pure math. Yeah.
Yeah. Okay. So this is just the basic kind of idea. So now we get into toruses, which are obviously can be turned into lattices, like of this kind. So we're kind of get back to the point a bit, I guess, of what I'm trying to get to. And then so we want the amplitude will be t, I believe. Yeah. But then this is in the time dimension, this is the space dimension, and this is the Lorentz lattice, effectively. So, yeah, so now you see where the cannonball problem kind of comes into it, where you have 24 dimensions, and then we have the light vector as well, but that's a separate issue. So we have the partition function, so we're summing from 0 to infinity, and we have the Euler equation with the, I guess this is the harmonic oscillators, you know, and the vacuum expectation value and all of that. And then when we sum that series, you get this. And yeah, and so we might come back to this, but so part of the point here is that, yeah, we have these kind of, how do you say, parallelograms on the lattice. So I kind of looked into that a bit, taking the parallelogram from here and then multiplying it or transforming it using something called, well, part of the SU2 transforms based on something called Arnold's cat, I think it's called. So we have the matrix, which are the basis vectors of the lattice, kind of, but transformed in a way so that these are like OR1, the complex version of the inner radius, the tube radius, and the radius of the torus that can be built out of the lattice. And then when we multiply a grid system by that, you get this. So it's the same lattice that we saw earlier, periodic lattice, but it's kind of skewed, so it's shifted. And this is kind of related to, if we look at the Lorentz lattice. So here we can see that as you move sort of in space, the thing and time, it gets shifted. And this kind of represents time dilation and length contraction. Okay, so that's the wrong one. Here we go. So skip this. So these are just other representations of the same thing, done in different ways. Oh yeah, so when we do that, we can look, we say it's shifted and it winds up at around this value, which is normalized. When we normalize it, it's 0.19247. Okay, so that means that when we've shifted the lattice at this length, we're basically moving at about 19.247% the speed of light. So that's just sort of a calculation we can make. Now we could also apply the lattice. So instead of using a lattice like this on A4 or I guess it's A4 or A6, it's A6 actually, we could use our original lattice, this lattice that we're interested in, or you know, to calculate the ground state. So use that lattice as the period lattice to do the bosonic string theory calculations. So that's what all of these equations are. And the main concept, I think, here is that when the lattice is this way, it should have the same area as if it's this way. And the only time that that happens is when you take the 24th power of this. So it's similar to how we were talking about minus 1/24th. We want it to be -1 because the lattice is supposed to be unimodular, as in it's supposed to be highly symmetric. So that's why we have this, like, if we have this equation, so it's I to the 20 divided by 24. So if we multiply that by 24, then it turns out correctly. I think is the concept.
It's almost like a gauge.
Oh, sorry, not multiply. Like, when you take the 24th degree, it does not change. You see, because it's.
Oh, so it's like a gauge transform.
In a sense, yeah, it would be. Yeah, this is all to do with gauge transformations on the. Yeah. You can read more about all of that and the gauge transformation part in this section. So, gauge symmetry, the ability to switch between different mathematical descriptions counts as the same physical situation. So exactly. So we're switching between this one, and we want to make sure that the value comes out the same. And if we just use this equation, they don't come out the same. But if we multiply or take the 24th degree, it is a gauge transformation. So that's what we're doing here. We're following all of that logic. So it should come out that at the end of this process, all the values are the same. And we can see we have two traces here, and they're overlapping. So they appear to be very similar. So this would be the ground state if you have, I don't know, what it is, 10 bosons, then 100,000, 10,000, 100,000, so on. So here's 10 bosons. So it says that the energy of this ground state is 4.16 times 10 to the minus 52, and so on and so forth. But you see the way it goes up, and then it goes back down, and then it goes up again. So I have no idea if this is correct. Also, so that's kind of why I'm bringing it up. Also, if you look, they're not identical. There is a slight difference. One is 4.16, the other one is 4.15, you know. So there's an issue there. So, I mean, one thing we could do is try and go through the maths and work out where I went wrong, but that might be a little bit tedious. But I have a feeling that this entire presentation is going to be a little bit tedious anyway, so it's up to you. So another thing that we can think of, so if we look back here, I think some of the comments mention, you know, what is the group law that determines what's going on in here? And you know, the group law would obviously be fairly complicated because this is an infinite number of points that are going around here. So it's difficult to know. So, but I'm interested in that question as well. So it's another kind of thing where I'm thinking of looking at. So let's imagine then that we're not looking at an infinite group, but that this lattice is also modulo itself. So when this dot goes out here, it comes in over here or up here or something. And same with this, you know, the opposite way for the other dots. So then we're only dealing with, I don't know, what is it, 7 across and 7 down, so 49.
Kind of like wrapping. Is it like wrapping? Kind of wraps around.
Yeah, exactly, yes. Or you can think of Pac-Man. Pac-Man goes out one side of the screen and in the other. So it's modular. So I mean, I guess we could move on to this then. So if we take a matrix in SU2, which has a determinant of 1, which is again linked back to this whole unimodular thing. We're talking about grid systems that have length 1, essentially. whether that's in 2 dimensions or 24 dimensions, it doesn't matter for this particular case. Then we modulo that 3. So we've got essentially we get a matrix in GL23, the general linear matrices of order 2 mod 3. And then we can graph these. Oh yeah, so then we can also apply our transformation function that we were using up here to shift the original lattice, period lattice, into this form, and then do that for all of the possible ranges, in a sense. So essentially recreate this. So instead of stopping when we get to a certain point, we just keep going round and around until it comes back to the same place. And it will come back to the same place because we're using a modular function here, as I said. So we can look at the results of that, and here we see we've just colored. So we're only using a 3x3 grid. Okay, so we've colored them. So this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9. And then if we apply the function, you can see here after 2 applications, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's backwards, yeah? So it has basically just reversed it by rotating it by 180 degrees. And if we look here, it's just rotated it by 90 degrees. And again, here it rotates it by, so this would be 270 degrees. And then it's back to where it started from. So after 4 applications, we get back to the start, which is again like an SU2 transformation. Okay, so if we have we have this like SU2 thing that keeps cropping up, which is to be expected. If we go back to the hypersphere of the universe that I'm proposing, so we have the projective point here, called P, and then we have the tangent space down here. So any of the galaxies here will be projected onto the tangent space. But I don't know, can I undo those last few? Okay, so, but let's imagine that we're traveling up the sphere here, we get to the projective point. But we could also have the projective point as an equator around the sphere, and then mirror everything that's in the universe the opposite way around. And so this would be our new projective point, in a sense. And then, since that works, because it's just the same as like traveling through the projective point to the other side of the universe. We just travel through, and we come out the other side. Okay, so that's the system here. But it would also have to be kind of flipped and inverted, because so almost like an SU2 transformation again. But if we can do that, if we can divide it that way, then each of these then becomes a fundamental domain. So we could potentially divide it an infinite number of times, kind of longitudinally. And then we can do the same latitudinally, obviously. We could just create fundamental domains this way as well. So we could have like an infinite number of those. And so I'm not sure if I'm presenting this in like the correct logical order of how I thought about it. But the basic concept is, let's say we're in this fundamental domain here, and then we start traveling at the speed of light. But if we were to go beyond the speed of light, we would reach the boundary of the fundamental domain. which means that we are already at the point, kind of the projective point up here, let's say, which would be an infinite point out here. So we're like completely squashed flat, and there's no time in some sense. So that would kind of equate to this boundary here. Then what happens if we go beyond the speed of light? Because that's kind of what this is suggesting here, is that, you know, like, let's look at this again. Let's wait until it gets to a point. Okay, so this is an A6 lattice. So when it's like that, when it's like a bit of a snowflake kind of, you know, that's when it's non-transformed in a sense. And then everything gets squashed. So those 4 dots that we said these are the 4 dots. They're getting more and more squashed. So time is becoming dilated and space is becoming contracted up to the point where it just becomes a straight line, and then you're on a light-like vector, so you're going at the speed of light. But if we look at the symmetries of this, it appears to come back around, you know, and become symmetric again with itself in the previous state every couple of times. But like I'm saying, if all of these dots are numbered and they're all modulo, then it doesn't come back around after like a second or two. It would come back. So in the case of a lattice with 9 points, it goes around 4 times before it comes back to the beginning. Yeah. So that's similar to fermions that need to be rotated pi4 before they come back to the start. So that could be like a kind of a link there between the fermion's spin and the general relativity kind of concept. But I'm sure that's all spoken about in stuff to do with string theory. It's a lot of that stuff is, you know, seems par for the course for this kind of field. So, but yeah, I mean, there is this video called "The Shape of Space," which might also explain a bit.
Stars are there? Does space go on forever? The answer depends on.
Can you hear that?
The shape of space. Let's explore some possibilities. There's an interesting star. This star looks familiar. Haven't we been here before? What's going on? What kind of space is this where we keep seeing the same stars again and again? It's easier to explain in a 2-dimensional universe than a 3D one. But what would a 2D universe be like? Let's call it flatland. Life in 2 dimensions has its problems. When 2 flatlanders want to pass one another, they can't go around each other or to the side as we would, since they can't leave the plane. Our athletic flatlanders must jump over one another to continue on their way.
Okay, so I might as well skip ahead through this, but you can kind of see here that it's talking about the similar thing that I'm kind of going on about, where you have these, what do you call them? Fundamental domains of space, essentially. So you go around, you come back to the start, and then they're using 2-dimensional representations in this, but later on, then they go into like a more 4-dimensional, or sorry, 3-dimensional version. So some of these visualizations are quite good.
And they see the back of their own spaceship. Like the flatlanders themselves, their line of sight can't leave their 2-dimensional space.
Okay. So then this creates.
They see what appears to be a copy of themselves. Indeed, they see images of themselves in many directions. This tile picture shows what the Flatlanders see, and that their universe is boundless. They'll never reach an edge. From the picture of the single fundamental domain, we see that their universe is not infinitely large. It contains only 3 stars and 1 spaceship. It's finite. Neither picture alone gives the full story. By combining these 2 pictures in your mind, you can get a better understanding of the true nature of their space. Now we're ready for 3 dimensions. Take a cubical block of space. We'll use this for our fundamental domain in 3 dimensions, just as we used a square in 2D. We glue the...
Okay, so we'll come back to that. So that gives you a bit of a visual background of what I was speaking about earlier. So now, because we're talking about Lorentz lattices and those transformations, we might as well look at what happens when we, let's say we go, we're traveling up to the speed of light. So here we're at, originally we were at 0, so we're not traveling at all. And then as we go up, get closer and closer to C, what this part of the graph here is explaining is the amount of time dilation we'd expect. So around here, I guess, time is dilated. Hang on a sec. Yeah, so let's look at this example. It seems a bit better. So at around here, time is dilated twice the speed, twice the length, I think. But then as you go closer and closer to the speed of light, it becomes undefined, so time stops. And then as you keep going faster, the solutions to the Lorentz equation, Lorentz transformation, are like, they become complex because they're the square root of a negative number. So then we move into imaginary time. And we see that if we keep traveling faster and faster beyond the speed of light, which was up there, it appears to go back down. So time would speed up in a sense, and it converges around 0.1. So time is therefore is contracted about 10 times the normal speed. So it's the opposite of dilated, so it's contracted, yeah. So if this is normal speed of time, it's 10 times faster, I think. Or is it 90 times faster? Yeah, so 0.9, that kind of thing. So gets a bit confusing. So the idea I was thinking of, well, what if as we go, it's a bit complicated to explain, but if this Lorentz lattice seems to suggest that time goes, it's going 1, 2, 3, 4, 5, 6, 7, 8, 9 here. So that's the correct order. That's time moving in a, how do you say, in a linear fashion from future or present to future, past to future, if you like. And here it's going 9, 8, 7, 6, 5, 4, 3, 2, 1. So it's going in reverse. So there's this idea that if you were to travel at the speed of light, time would stop. But if you were to travel beyond it, time would reverse, which makes sense because you're kind of catching up on the light rays, and then you'd see it all happening in reverse. But then what does this mean? Because this is a 90-degree turn. It's instead going, if we were to count normally, it would go 3, 6, 9, 2, 5, 8, 1, 4, 7. So what kind of time is that? It's no longer linear. Everything is out of joint. So this would be, this is equivalent to a rotation which could be described, because we have 4 different rotations. So one of these could be described by, for instance, this is times 1, just the identity. This is times -1 because it's backwards. And so this is times the imaginary unit, I, and this is the backwards version of that, so it's -I. So now I think we're beginning to get a sense of what I'm talking about. We have forward time, then we have a superluminal backwards time, and then we have a forwards imaginary time, and then a superluminal forwards imaginary time, and a superluminal backwards imaginary time. So this picture, therefore, is wrong, I'm suggesting, because we have forwards time, then we have the backwards imaginary time, which just seems to stretch to infinity from that point on. And there seems to be something kind of asymmetric about this picture, like very asymmetric. It's like this, if this goes on for infinity, like if such a thing as infinity speed were to exist just for the sake of argument, then this point here vanishes to nothing and like it really just doesn't exist. Yet this is where everything in the universe happens. So that's odd. So I thought, well, since we applied, you know, a mod 3 to the lattice to make it conform to a toroidal lattice that loops on itself, then we could similarly apply mod 3 to traveling at the speed of light, if you like. So when we do that, well, we lose a lot of data because the imaginary curve, it just wasn't picked up in this particular example. You see it's all not a number, or infinity. So we have to do some, there's the mod 3, you see, and we have to do some, if it is an and, then we take the absolute imaginary value, else just output the real value. And then when we do that, we get this. So here's traveling up to the speed of light. This is the imaginary speed of light. Then we flick into the next modular section. So we go back to building up to speed of light and then imaginary again, and so on and so forth. But we see that there's a disconnect here. There's obviously a disconnect here because we go to infinity, but there's no infinity here because we've already passed 0 speed. So, or well, not 0 speed, but normal time. We're now time is speeding up, possibly going backwards as well. And then there's a jump back to time, kind of being slower again. So that doesn't feel right. So there's obviously something missing here. So my solution to that is to, yeah.
Is that possible that one of them describes the particle, that the particle, you know, starts speed and then reaches speed of light, then the wave, which, you know, in the case of wave, the time is probably imaginary. You know, is it possible? One is the particle and then it becomes the wave aspect.
Oh,
like
yeah, I
that.
see what you mean. I don't know, because I mean that's a bit weird. That's, yeah, I know what you're saying. Possibly. I mean, we can look into some other ideas around that kind of thing. I mean, if I was to just attempt to maybe give a counter argument to that, like if we're not looking at a particle, then it's a wave, yeah? There's a wave nature to it. It could be in lots of different places at once. And that in itself is a kind of a superluminal quality. But why does looking at something then fix it here? And also remember, we're traveling, if this is C, this would be 2C. So we're at this point, we're going twice the speed of light, and we're no longer in imaginary time. You see? And here we're going 3 times the speed of light, and we're back to imaginary, and then 4 times, and we're in real time again. So if it was the case that, let's say, a particle could travel faster than the speed of light, then it would go into imaginary time. It would become a wave, yeah. But then if it went 4 times the speed, or 3 times the speed of light, it would become a particle again. So yeah, that's interesting. Maybe there's some symmetry there. But like I say, so there's a problem here. There's a disjoint, and that needs to be solved. So my method of solving it was to say, you know, we're traveling at 10% the speed of light here, 20, 30, 40. So there's the speed of light, and then we keep going up to 10 times the speed of light. But what we want to do is create a kind of we want to express the fact that time reverses and then goes into imaginary time, if you like, and then which happens through the Lorentz transformation, and then reversed imaginary time. So to do that, I just literally I took the speeds, and when you get up to a certain point, like 2.9, it starts going in reverse. So then we go 2.8, 2.7, and so on and so forth, and then it reverses again later on and again, and then we take the mod 3 of that and get all the complex values and graph that, and this is what we get. So this is real time, then into imaginary time. Now I'm pretty sure this is backwards imaginary time, then forwards imaginary time, then backwards real time, forwards real time, and backwards imaginary time again, and it just repeats like that to infinity. So that's my that's what I'm thinking. So now we have 4 different things. It's not just 2. It's not simply, is it a particle or is it a wave? It's, is it a particle that's traveling? You know, it could be, is it a particle? Is it an antiparticle? Is it a wave? Is it an anti-wave? Maybe that could be the question. Or we could, once again, we're kind of back to the SU2 thing. So I think this graph here is really another expression of these particle Lorentz lattices that we were talking about, which are like wrapped up toroids. And then, of course, we could ask the question, and there's something kind of oddly familiar about this shape that's being created. Kind of reminds me a bit of, I don't know, is there like, is it a 3D Riemann surface? Somewhere? Maybe not. Oh, I spelled Riemann wrong again. Okay, and put that in there. I don't know. 3D modular form. There, this image. So perhaps it's something related to this, you know? I don't know though. I haven't found out enough about it yet to say for sure. So, going back to this, and maybe, excuse me, maybe tying it into your work a bit, Rajan. Now, I know you're dealing with 6 dimensions of time, and I think that the thing you're looking at solving is this symmetry between time and like the momentum symmetry. Oh, do you need to take a break or anything?
Is it? It's 10 o'clock. Yeah, after 10 minutes we can take a break, and
Okay.
then we may knock it off. Probably another hour or something can do, but we can take a break and then do another 1 hour. But one of the things I was thinking recently is, I'm glad that you brought it up. And also, I just want to bring out, sorry that I interrupted you. Last time you said that I like the way you presented, but I interrupted you. I think, the way, so I didn't, I mean, we can talk about later, but I think you are talking about my presentation
Oh,
last time.
I'm not sure. Yeah,
So I think
remind me of
the
that.
two
I have no
episodes.
recollection of it, but yeah. So well, just to finish up here then, because we're kind of coming to the end of the, I'd say, of most
Okay.
of the things that I'm trying to get across. So you're talking about there's the momentum, and you're looking for a symmetry.
Yeah.
Essentially, is it like Noether's symmetry?
The conservation. See,
That's the one.
I presented last time that thermodynamics is very clear about the conservation of energy. But, actually Maxwell also worked with thermodynamics, like I pointed out last time. So when I went through the research, I found, I know that there were Maxwell equations in thermodynamics, but when I went through the research, which I presented last time, which is more, I think more historical, probably little more accurate, is that Maxwell was very much was one of the architects of the thermodynamics behind the scenes. But what they found was conservation energy is something they can actually pinpoint and actually prove, at least
Yeah.
in our part of the universe. But the momentum conservation is something that was not possible, and Maxwell took up on that, and he found that it's not really possible. He found the speed of the speed distribution, things like that.
Yeah.
And finally, he came up with the idea of fields. That's when he came that, okay, then he had, then he put together all the Gauss and, Faraday and all those people, and then even Ampere. And then he found that there's a displacement current when he did the math. So when he put all these together, he found that the speed of light, and at that time, they measured the speed of light. So he found the physics, he saw the connection, and he said that maybe the field is conserved, but actually he couldn't prove that field conservation doesn't even apply to the fields.
Yeah.
So I mean that was a limbo. The problem, I think, he carried over to the standard model, and still that's problem. And even the dark energy, I found the recent yesterday, a couple of few days ago, I
Yeah.
found that the dark energy is supposed to say that the force is constant, but actually they say it's not constant. So
Which
there is a
force?
big problem.
The dark energy or dark
Dark
matter?
energy, dark energy.
Oh, because it's not
dark,
constant because the universe is expanding at accelerated rate. Is that it?
yeah.
Well,
I mean,
I don't know. I mean, obviously, my research is kind of fringe, but I think through which was the one that disproved the oh, it's this one seems to suggest there's no
Maragani. Okay.
Yeah, well, the cosmological constant problem, is it well, anyway, basically it looks like there's no dark energy in my model anyway, so and there's no accelerated expansion of the universe. And I think that's been disproven anyway recently. They took more data because the original measurement was taken using only like a small number of galaxies, and then they redid it a couple of years back with a larger number of galaxies, and the effect went away. But they still hold that the universe is expanding, and that's, I think, open to debate, but it's not necessarily wrong. But in my model, obviously, the universe did expand at a certain point, to its current size, but then it stopped expanding. Oh, Rajan, would you be able to close your door? There's like there's a bit of interference.
What door? It's kind of closed. I can close it completely. Hold on.
Oh, that'd be good, because I thought someone was talking to you, but then by the sounds of it, they're just outside the room talking or whatever. Okay, so let me think. That's better now. So what I'm trying to get at then, so if you have these 6 dimensions of time, and I know you're trying to apply it to this conservation law now, so that's interesting. I think I picked that up in the last talk you gave, the episode. So, or I kind of knew it anyway, but yeah. So what am I trying to get at is, like, if we think of these lattice transformations, okay, so this was minus 1. Where did minus 1 go? This was 1. This was I. This was minus 1, and that's minus I. So those are obviously matrices that can be found in this group here, GL23. We have, if I scroll down, we have 1, minus 1, I, and minus I. And we can see that the actions that they have, 1 does nothing, minus 1 reverses them all, I moves them 40 degrees, or what am I saying, 90 degrees to the left, and minus I 90 degrees to the right. Or another way of saying that is 270 degrees to the left. You know, so
are they isomorphic? Are they isomorphic, or do they change? Do they change the structure or the shape? The shape? Do they change the shape? You know, isomorphic means
it's a rotation. It's a rotation, Rajan. So, like I showed here, if
gauge, gauge symmetry.
Yeah, because here we're seeing
symmetry.
This is 1 starting in the bottom left-hand corner here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it just rotates it. You see, it's rotating it 90 degrees and 90 degrees again and 90 degrees again. So it's kind of you know, and then once you apply it again, it's going to come back to the start. So yeah, there'll be a lot of symmetry there, but we can see that those 4 are only like 4 out of the total 24 that are in, let's say, SL2Z, C or C. So, or is it 2Z or is it 2Z? It's hard to know sometimes, but right. So anyway, it doesn't matter, I don't think, for the purpose of this argument. So, but the point I'm trying to make is, so you might have these groups of 4 that transform the Lorentz lattice in specific ways that I think will only become, or that will become more obvious if we were to transform instead a 2D 3x3 plane. If we transformed a 3D grid using those matrices, we'd be able to see which ones rotate 90 degrees to the right, which ones rotate 90 degrees to the left in the XY axis, and which ones do the same thing in the Z axis, and then group them together as like, okay, so they do that with these axes, and these are the results we'd expect from them. But so one thing that is true, though, is that these matrices are all grouped into 4. So for instance, if we take 1, I, J, and K, those are the quaternions, yeah? So that's going to be one group of 4 in a sense. Or actually, better yet, let's take this group here, this one, and this one, and this one. So that's plus J, plus K, minus J, minus K. So that would be a group. But maybe that's not the right. I mean, it's a group because they all look the same and they all produce I think they produce magic squares. Not sure. These definitely produce magic squares. So this could be a group 1, 2, 3, 4 because they all look the same. They also look a bit like, what is it in kanji? Is it in Japanese culture? And you guys have it as well.
Oh, okay.
Yeah.
Yeah.
And then here we have this one is like the Star of David, you know? So everyone's represented. We're happy. Anyway, moving on. Yeah, and then even here, you know, the Muslims are big into their 4.
Oh, yeah.
Yeah. And this could be like a cross, I guess. So anyways, that's actually important. And then so anyways, that's not relevant really to the point. It's just a bit of a fun aside. What is
like
the point?
Similar pattern
Yes.
similarity.
So we've got IJK and 1. Those constitute the quaternions, and they're rotations in 4-dimensional space. Fine. And then we can imagine then that there are other groups of 4 that handle different dimensional spaces that we won't understand, but that may come into play when we're talking about superluminal speeds. So, for example, this universe here that we're in, when we're going faster than the speed of light, has a different set of rotations to this one when we're going backwards, and this one when we're, you know, so on and so forth. That was really what I was trying to get at in this video.
Left and right walls. Now the spaceship can travel around this finite universe, passing.
So when it goes through the wall, it's gone at the speed of light, you know, because it's gone flat.
The same stars again and again.
Okay. And when it comes back to the center, then it's slowed back down. Okay. And it doesn't matter which direction it travels, that's all the same.
Like hyperspace type of thing.
Well, this is actually just 3D space, but it's tiled. Because like as he travels through, remember what they said, he can see the back of the spacecraft because the light rays can go through the walls. So the light rays can, if we were to continue with my analogy, they could travel through into the next universe, but that's not actually the case. That's why we can't see
like
the next.
Star Wars, Star Trek or Star Wars type thing. Yeah.
Kind of like a warp thing, maybe. Yeah, we might get to that. But we cannot. It's not to do with warp space or anything like that. So the point I'm making is, if we go back here, this is our entire universe, and I think I mentioned it here that the band. So each of those blocks, that this fundamental domain is equivalent to this square here, let's say. So our entire universe is contained in this square, and the boundary of this is our original projective point at the North Pole. So that's our new boundary, projective point. So if we were to travel at the speed of light, you could get, you know, it's not true that you could reach the boundary at the speed of light. It's more complicated than that, but let's just pretend that that is true. When you get to here, you reach a boundary, or maybe it is true. Maybe as you travel, the fundamental domain gets smaller and you're able to reach the boundary. And then if you're to go faster than the speed of light, you would go out here. But the point I'm trying to make is that the light should never cross the boundary. So we'll never be able to get into the next fundamental domain. So you'll never see copies of yourself. You'll never see copies of the universe, which is what you're seeing here, because they remove the walls. The light can travel through the wall, so you see the back of your own spacecraft.
It's like a reflection.
Kind of, yeah. Or it's, well, look at it this way. See the torus, see the way that spacecraft is here, and the light leaves the spacecraft and goes around, all the way around space, and comes out the back. So you see yourself.
Wrapped around, kind of.
Yeah,
wrapping around. The light kind of wraps around.
Exactly. So that's more what it is. It's less like a reflection, more like a wraparound. Okay, so let's get back to this video. Where were we in it? Yeah, I think around here.
They see infinitely many images of their universe, half reversed and half not.
So this is when you apply a Mobius strip. So you create a universe with a Mobius strip.
Let's watch the trip again on the original square.
So we see now, in order to get back to its original position, it had to travel through once, twice, 2 times. So it had to do 2 rotations to get back to itself. So again, this is fermionic. It's SU2 rotations, right? So now we can do it in 3D.
To the bottom of the left face and vice versa.
Comes out upside down. So this is like real time, going faster, approaching the speed of light, reaching the speed of light, going into imaginary time. Now you're upside down, and time is reversed. You keep going.
After one trip, the spaceship appears mirror reversed.
Now now time is going backwards. Imaginary time is going backwards.
After a second.
And now you're back to basically standing still, or no. Sorry, now real time is going backwards.
Trip, it returns to its original state.
And now you're standing still, but you're not standing still. You're now going at.
It can go to another universe. Is it like a multiverse or something?
Well, this is
like
this
go to
is
another
it.
universe.
Because these fundamental domains should all be the same, yeah, because they're all copies of themselves. But if it was based on this SU2, if it's based on what I'm talking about here, which has this SU2 transformation, then it seems that this is actually a Mobius strip, in a sense. And so this universe here is inverted to this universe, just like we saw in the video where the first spacecraft is upside down. So it's inverted. Everything would be the opposite way around. So when you travel, if you were to travel from stationary, you go at the speed of light, you would literally turn inside out, time would reverse, and then time would go back, and then you would, but you turn inside out in a particular way, like you wouldn't die or anything, you'd just be reversed. Everything would be, it would be a mirror universe, yeah?
Oh, yeah.
Yeah, so...
I was proposing that much earlier, like more than 20 years, 30 years ago.
Oh,
I
yeah,
think,
yeah.
When I did the initial calculation, I said it should be a mirror universe. Something
okay,
that,
but I'll bet you approached it, you had a completely different...
yeah. Different
approach.
I mean, it's more physics than math, you know.
Very good, very good.
I mean, I used, because I never used this light of math earlier. It was much simpler math I used. So, but more like physics or materials type of thing.
Great. I mean, if you arrive at the same answers, then that's a good sign that you're on the right track.
Yeah.
That's assuming that I'm on the right track. Anyway.
Yeah.
Okay, so let me think. So the point I think I'm trying to get to, I think I've covered everything now, but so if we have these 4 transformations which deal with fermion, they deal with superluminal travel, they deal with the hyperdimensions and the mirror universes, then we're talking about extra dimensions, other universes, and we're also tying in string theory with the 24 dimensions, and we have these 24 particles or dimensions in the GL or SL2C. So the end result is that we could partition the 24 particles into 24 divided by 4, which would give us 6, yeah? So that would be 6 independent universes with independent rotations, you know? So each of like 4 dimensions in a sense. So when I thought of that, I was like, oh yeah, that kind of links back to your work with 6 different times.
Rank 6. Yeah, rank 6 tensor.
Yeah.
Rank 6 time tensor, yeah.
So instead of having I'm thinking that a possible modification to your theory could be to do with the idea that instead of it being like 6 different, and well, it's not that much of a modification though, because you'd be talking about how time changes as you move, you know, at the speed of light, maybe even beyond the speed of light. And if that's the case, then the two could be identical, because we're you know, or the two could be you could be merged in this scheme, under this schema, I guess. So then but the interesting thing is, right, imagine we have these 6 universes and they all have like within them there are 4 so like let's say our universe is typified by I, J, K, and 1. So the quaternions, yeah? And those are the 4 dimensions needed to build the hypersphere and the tangent space. So we only see 3 of those dimensions, but there are 4 of them do exist. And then the backwards universe, where time is running backwards, not imaginary, but just literally backwards, would be oh, wrong one. Would just be -1 minus J minus K. So that's another universe. And then we'd have what's that? 2 unit. So we'd have 4 more universes, but they would have weird
permutation. It's like permutation of that.
Right. It's more than that though, because it's a combination. It's
combinatory.
So let's say we have 4 that we picked these 4, didn't we? Let's go with the Stars of David one. So one of them is 1 minus I plus J plus K. Another one is, so yeah, it's a permutation in the sense of permutation of the signs.
The 4 of them.
Yeah,
the 4 of them.
4 of them together and then permutated. Yeah, but you could say the same here. This could be 0, 0, 0 minus I, or sorry, 0 minus I 0, 0. You know, it's just here that they happen to be, all 4 of them are here, and so it's a permutation of sign at this point, and it's also divided by 2. But we don't. That doesn't need to be there. That we can leave that out, to make things simpler, and also because probably more correct. So yeah, if simply changing the sign reverses time, then these other ones, what would they do? Like, what results would they have on the lattice? So in order to figure that out, we would have to create the 3-dimensional lattice, as I said before, and start multiplying, transforming them using these equations, but instead of using whichever ones I used here, which I think was the lattice that I showed earlier, transformation, you would use the SL2Z matrices, and then you would have the transformations of the Lorentz lattice transformations for each of the 6 different dimensions. And then you'd be able to talk about how does time transform in those dimensions, or how does space transform. Maybe that's a better way of going about it. So the question is then, because there are 6 different universes, does that mean they have 6 different times? And that's a kind of a question. Like, if we think about a 3-dimensional universe that has 3 different dimensions, then we talk about time in that universe. And suppose we're not moving, we're just sitting still, then would we say that there's time on each axis? Maybe. I mean,
the tensor time means there are 2 aspects of time. One is a scalar aspect, the other one is the vector aspect. So the vector aspect, it can go positive and negative, right? It can go positive and negative. The scalar aspect goes only one way. Like we track our time, it goes only one way. Like today, like AM. Right now, maybe like 10 something here, AM. Yeah. Then it moves. It doesn't go back.
Okay, so one of them could be like time reversible, like on the quantum scale is a vector time.
Exactly.
Okay, so yeah, So I don't think, because I thought about this and I was like, oh, okay, maybe that could connect to Rajan's thing. But then when you started talking about conservation laws of momentum, I was like, oh, that's not going to work. And then now that you specified that, that's a bit more, that's clearer now to me on that front. But you do have then scalar, then vector, then matrix, right?
Yeah, yeah,
Rank 2 tensor, which are all of these. So
yeah.
this would be like, how is our little Lorentz lattice 3x3 transforming in, you know, with this tensor? Well, it's going in this weird way. And what does that? Well, what would that mean for the people living in that dimension, or is it?
Yeah.
Is it something that we could see in this dimension? And is that just then the expression of how the particle transforms inside its own torus shape, if you like, or lattice?
Yeah, yeah.
So yes, but then I was also thinking that it probably, you know, there's another issue, I guess, but mainly like, is it right to say that there are 6 dimensions of time for each of these different universes? Because maybe the 6 universes, they all have the same time, you know, in a sense. But it's just
4. You mean 4 universes? 4 universes.
No.
4 times 6, right?
Right. You see, this is what I was thinking about, because you had the idea of 6 times and 4 spatial dimensions.
Dimension, because you have 4 dimensions, like torus or something.
Yes.
4 dimensions.
4 dimensions. So 6 times 4 gives you 24. So then when I was thinking that, I was like, oh yeah, that's what Rajan's been going on about. So there's definitely a link. But you just said, what did you say there? 6 time dimensions or 6 space dimensions?
6 time.
Yes, 6 time
6
dimensions.
Time.
But 6 time dimensions times the 4 spatial.
They're not really dimensions. They are not really dimensions in the normal sense, like we talked earlier. So it's kind of like, you know, you can put in quotes or virtual dimensions, but they're not geometric dimensions.
No, I was just trying to see if I could find a connection. But in this, okay, but by doing so, I found something else now. I don't think it probably isn't worth publishing, but it does kind of link back to some of maybe the more Eastern schools of thought. Certainly, I know Buddhism emerged from India, right? But then it was exported, went to China, and in particular to Tibet. And the Tibetans had their own sort of shamanic religion, which spoke of these 6 different worlds, and called bardos. So I just think it's interesting that this could kind of, in a weird way, confirm what they're saying, that there's these like 6 different realities that coexist. But each one would be like 4 dimensions, because they'd each have a sphere and they'd each have a tangent plane related to them. But
it's a nice picture you have. Yeah.
The one I've just drawn, or the concept that I've come up with.
The concept, the concept.
Oh, cool. Yeah, so that's what I've been thinking about recently, and I'm glad I got some nice results out of, you know, actually I got some visual results and a bit of application. So that's really it. So this is kind of sitting here ready to go. We can start to make the 3-dimensional ones at a later stage. We looked at the cool video with the kind of scary music, and that's it. So do you want to take a quick break?
Yeah. Just a couple of things, maybe another 5 minutes. Just to recap, one of the things I thinking recently is that from the I'm glad that you brought some thing that we can work on. We are converging on something, but the important thing is that from the general transforms, I come up with some that the universe is like a black box. So I was thinking about that.
Yeah.
Black box means we cannot. It doesn't have any. We cannot put any diamond. Any what we call the size. We cannot put any limit on the size. So black box means it could be very small. It could be very large. So our thought process, then how small it can be. So I can bring in Christian's thing that you cannot have zero. So it has to be greater than zero. That makes sense. So the
Yeah.
smallest box can be like a Planck box. I was thinking like a Planck box, and there could be only one particle in there, right?
Okay.
But that box, we can think of that box does not have any dimension. So which means that it could have been almost infinite size and still have only one particle. And I was thinking that that may be the reason the inflation theory came to be. Of course, right now, Turek, everybody now thinks that that's not really panning out to be correct. The inflation theory may not work
Yeah.
out, but I'm thinking that that may be where it comes out, which means
No,
that, we
inflation theory did not.
really.
I don't think so. I don't think. I mean, you could relate it to it, but I don't think that was the reason why they created inflation theory. There was a number of reasons. I know that it explained why there's no magnetic monopoles for a start. Because they'd all be pushed out to the edge of the universe.
Yeah,
But I think it was more to do with, gosh, I've forgotten exactly why they brought it up.
Is it based on the expansion of the universe? They're applying the expansion. So that if you are to scale back expansion of the universe, it all goes to one point, right? I mean, if you trace back to the beginning of the Big Bang, then it should be all at one point. Then it is expanded to balloon. It's like ballooning effect.
Right,
it could be that
inflation happened before the Big Bang, or like maybe at the same time. But is it? I've actually forgotten because, well, like in some sense, I don't need to know about inflation theory because A, like you said, it seems to be disproven. B, it's not part of my model, and it's disproven in my model. And so you know, at a certain point, you just like if something is like not like we might as well be talking about phlogiston, or or even maybe ether in some circles. But so once something is just wrong, I just drop it. But like obviously, there's people picking holes in string theory and saying string theory is wrong. But I still think there's like a lot of cool maths and ideas. That we still
I agree.
Still work with string theory.
You can use the concept. I use them. So the key thing I'm saying is that that comes back to the idea of time. The time I'm talking about, the time tensor. And then I'm glad that we have some common points in there. So one of the things I was thinking is that what happens the time. Of course, eventually you have to do the umbrella model, things like that, to really understand the physics of it. But the thing is that what is happening is that we have, at some point, we are looking at the vector time. The umbrella is open, so it's vector. But then it closes, and then you get the zero tensor, which is scalar. So we have finally closes. It gets rank 1, which is vector, which points to rank 0, which is a scalar. And that's what the real universe. Then we see the real universe, observable universe. Then we are, our consciousness tells what we are seeing is what it is. So sometimes our consciousness.
I'm not sure if I agree, but it's interesting. I think, it's more kind of mystical or something. I do like the way you're bringing consciousness into it. I think that's worth doing. I would be. I think if you're going to do that, you're going to have to be really kind of more rigorous. And
that's what I'm thinking.
You totally should do that. I think it's pretty cool, and you've got the tensors, and you're working on that. There's another guy called Christopher Langen. Have you heard of him?
Kind of, yeah. I think that sounds familiar.
A few times the CTMU theory. This guy Christopher Langen, and he. Oh yeah, watch that one. This is Theories of Everything with Kurt J. Mungle. I was telling you about him as well. But that's a very good interview. It's like an hour or 2 hours long, and he goes into it all. And he's got a lot of
cognitive theoretic model
of the universe. Yeah, check that out. He's really he seems to be bringing consciousness into like it says right there, cognitive theory model of the universe. So. And it's probably the best model. But I do like, you were talking about stuff like sense, was it?
Yeah.
You had sense.
Yeah, the field. Sense give the field sense to time. In one paper I have in CJ Pass, I have 4 papers. I think they are really, I consider one of the top ones because they bring out the key aspect. And one of them is that the sense field, where I have almost proven, at least conceptually, that the sense actually gives field effect to time, in the quantum at certain levels, like in macroscopic, it gives the sense gives field effect to both time and space.
Yeah. Well, so yeah, like I'm not like, again, that would need to be like more rigorous or something.
Yeah.
For me to follow, but I was thinking, it's pretty cool that you have this kind of like sense, which kind of goes back to consciousness, and then you have a field. I was thinking, you could that there's other kinds of fields. You could have like, what do you call, like a field of intention? So, so when you intend to do something, it kind of generates a field that makes the probability of that thing that you're going to do more probable, or something, even if it's something ridiculous.
Interesting.
And then the more you do it, the stronger the field gets. So the more likely it's going to happen. So there was like a universe where it was like basically not possible, and then it comes into being. And then on another, so then you could have like, maybe you could bring the scalar vector thing into that, because if we can, wait a second, you got to listen to what I'm saying before you respond. Just give me a second. So then imagine like you have a the concept of free will, and the fact, like if we were to think of some of the physicists, was it Wheeler or the Navier-Stokes formula, and Newton, who said, like, if you tell me the position and trajectory of a particle or system of particles, I can tell you what's going to happen in the future. So if I knew the position and trajectory, I think, of every particle in the universe, he could predict what the universe would look like at any point in time, So then the idea of free will kind of seems to go out the window. But that's merely the particles and the physical things. We don't have a physical or we don't have a mathematical description of what humans do. Now you could say, well, I could model the particles in your brain and the synapses and be able to predict what you're going to do as well, but that's not true, because we can't use simple differential equations to solve that problem. We have no idea if that's even applicable, because in that domain of consciousness. So but what if there's the universe, and it seems inevitable, on some level, on some non-scientific philosophical level, possibly metaphysical level, that there's no such thing as free will, and then in that case, then humans do not have free will. But if we have this thing called an intention field, which is capable of generating things that are not possible in the universe, or highly improbable is probably a better way of saying it, then we could imagine that on a larger scale, the scale of the entire human, when taking in all the, more than the sum of its parts, essentially, that it generates this field that is capable of creating something outside of the universe. So therefore, no longer bound by the simple cause and effect laws of the universe, and therefore that intention can kind of transcend those laws and thereby reinstate not determinism, but free will. So, and I'm pretty sure if you watch the CTMU, this one, but not, that's just a snippet, but the entire one, wherever it is, you will find that he mentions that he believes in free will as well. So, what is that? 2 out of 10. All right. Okay, so there you go. That's just my thinking on that. That might be something worthwhile as well for you to investigate.
Yeah. I think one good thing about the core universe model is I think it retains the idea of free will, because you're thinking in this part, and then time is in one state, and the other one time is in different state, which means there is a degree of freedom that makes the free will possible, in the sense that something can happen in this universe independent of the other universe, which means your mind is here, but you can switch to the other one. That you have free will. In the other universe, you can do something else. So you are not bound by the laws of the one universe. You know what I mean? So you can transcend that. In that sense, you can transcend that. And that question is the question of matrix. People think it's like a matrix. There's a matrix theory which says the whole universe is a matrix. It's a simulation, matrix simulation.
Oh, that
There's
kind of
one, matrix simulation, right? But that's only applicable to that universe. But there is another universe independent of that, and there may be mirror universe and things like that.
Yes.
That opens the possibility of having consciousness or also free will, and also having the matrix universe. I think it kind of is a multiverse idea, but multiverse is limited to 4 universes. It's not infinite universe, but it could be like 4 universe.
I don't know. It's only limited to 4. Because 6
and then you have
universes. There's 6 time dimensions, therefore 4 universes.
Yeah.
Okay. Whereas I'm looking at it the other way around. Wait a second. I'm looking at it as, I'm gonna have to think about that, because I'm saying there's 6 universes.
No, your plot shows only 4 universes, realistically, because you have these.
No,
only
but
four different
Rajan, think about this, right? In our universe, let's even just go. Let's go with like Einstein's 4-dimensional universe. Even though in the Ohm universe it's 4 spatial dimensions, but let's just say we're talking about Einstein's 4-dimensional universe. Then, if you have that, you have 4, and then those 4 that are going to be these groups of transformation matrices, which would be the quaternions, which makes sense because that's this, the metric tensor for Einstein, the stress energy tensor and all that. They're kind of, how do you say, they're kind of quaternion in a sense, because you've like 1 for time and then -1 for the other 3. So that's a quaternionic matrix. Or multiplication. Anyway, so when we do that, we have 4 dimensions there, and then we multiply by 6 to get the 24. And then since our entire universe is made up of 3 space and 1 time, then that would be 6 copies of that. So that would be 6 universes. Get it? And it would also have 6, interestingly enough, in that situation, you would also have 6 time dimensions. You see? Because 6 universes, each with their own times, 6 time dimensions. Yeah?
36 becomes 36.
How does it become 36? Oh, 6 by 6.
6 times 6. It
Well,
could be true. I mean,
why would you multiply each of the times? It could just be 1, though. It could just be 1 time because they could all share the same time. You know,
possible.
Well,
I don't know about that.
It's interesting. Yeah. Anyways, okay, we'll take a break.
Yeah,
there.
it's possible. Yeah. Okay. Yeah, we'll take, and then we'll try to finish off pretty fast.
Well, yeah, we can actually. Yeah, I mean, do you want to just end it there, or?
We can spend another 10 minutes and then call it off, maybe, if you want to.
Yeah. Well, we're going to take a break.
Yeah.
Okay.
Yeah, we can take a break and then come back. Okay. And then we'll finish it. Thank you.
Is, how many stars are there? Does space go on forever? The answer depends on the shape of space. Let's explore some possibilities. There's an interesting star. This star looks familiar. Haven't we been here before? What's going on? What kind of space is this where we keep seeing the same stars again and again? It's easier to explain in a 2-dimensional universe than a 3D one. But what would a 2D universe be like? Let's call it flatland. Life in 2 dimensions has its problems. When 2 flatlanders want to pass one another, they can't go around each other or to the side as we would, since they can't leave the plane. Our athletic flatlanders must jump over one another to continue on their way. The flatlanders live on the 1-dimensional surface of their 2-dimensional planet, just as we spacelanders live on the 2D surface of our 3D planet. The flatlanders' planet is orbiting a sun. Their sun is a 2-dimensional disk, just as our sun is a 3-dimensional ball. Like ours, their sun is just one of many stars in their universe. Let's watch the flatlanders explore their universe. They head straight off into space and are surprised to come across their own sun. Perhaps their universe is a sphere and they took a trip around its equator. Or perhaps it's a cylinder. Or a torus. Each of these surfaces is a possible shape for a 2-dimensional universe. Note that we have taken advantage of our 3-dimensional space to see something that 2-dimensional flatlanders can't see directly. In a similar way, 4-dimensional people could draw 3-dimensional universes in their space, but that's another video. We 3-dimensional people can see them without the 4th dimension. We can visualize 3D spaces using only 3 dimensions for our drawings. We first try to understand a flatlander's universe without the extra dimension. Suppose their universe is a torus. We'll save a copy of it, cut the torus once, and deform it into a cylinder. Cut it again, open it into a square. This square is a fundamental domain for the Flatlanders' universe. We now see their universe using only 2 dimensions. The Flatlanders can still travel about their universe as before. When looking at a fundamental domain, we must imagine that its edges are glued together. Anything leaving one glued edge returns at the other. The way we glue them determines the shape of the space. It doesn't matter where we put the cuts. We need cuts to draw the fundamental domain, but they don't really exist in the space itself. When our cut passes through the Flatlanders, they don't feel a thing. What do the Flatlanders see in this universe? Their line of sight travels around the universe, and they see the back of their own spaceship. Like the Flatlanders themselves, their line of sight can't leave their 2-dimensional space. They see what appears to be a copy of themselves. Indeed, they see images of themselves in many directions. This tile picture shows what the Flatlanders see, and that their universe is boundless. They'll never reach an edge. From the picture of the single fundamental domain, we see that their universe is not infinitely large. It contains only 3 stars and 1 spaceship. It's finite. Neither picture alone gives the full story. By combining these 2 pictures in your mind, you can get a better understanding of the true nature of their space. Now we're ready for 3 dimensions. Take a cubical block of space. We'll use this for our fundamental domain in 3 dimensions, just as we used a square in 2D. We glue the left and right walls. Now the spaceship can travel around this finite universe, passing the same stars again and again. We glue the top and bottom. And finally glue the back to the front. Now the space has no boundary and the ship can travel in any direction. This space is called a 3 torus. Let's ride the spaceship inside the 3 torus. Even though the 3 torus is finite, we have the illusion of flying in an infinite space. There are only 2 stars in this universe, but we see each one over and over. This isn't the only possible shape for space. Before we visit another 3D universe, we'll look at the corresponding 2-dimensional space. Its fundamental domain is again a square. This time we glue the left and right sides with a flip. This surface is called a Möbius strip. When the spaceship takes a trip around, it comes back upside down. The flip makes a difference in the shape of space. A second trip restores it to its original condition. Let's watch the trip again on the original square. Now glue the top and bottom of the square with no flip. What do the Flatlanders see in this space? Looking up, they see the bottom of their own spaceship. Looking forward, they don't see their ship right in front of themselves because of the flip. Their line of sight keeps going across the bottom. When it wraps around a second time, it's flipped again, and they finally see the back of their own ship. The Flatlanders have the illusion of seeing a reverse copy of their universe, followed by a regular one. They see infinitely many images of their universe, half reversed and half not. What if we do this in 3D? Two pairs of faces connect as in the 3 torus. To make the flip, connect the top of the right face to the bottom of the left face, and vice versa. After one trip, the spaceship appears mirror reversed. After a second trip, it returns to its original state. Let's see what this space looks like from the inside. As in 2D, we see infinitely many images of our ship. Half are mirror reversed, half are not. When we roll, our reversed images roll in the opposite direction. Life in this space is different than in the 3 torus, where all the copies of the ship move in the same direction, like a flock of birds. We fly this way and see ships in neighboring rows flying in the opposite direction. The mirrored images turn as we do to fly along paths that seem to cross ours, but they can never hit us. That's impossible in this space. We've looked at only a few of the many possible shapes for space. There are other ways to glue the walls of a cube together. Or instead of a cube, we could use a different shape for the fundamental domain. The space we saw at the beginning of this video was really a 3 torus containing only 96 stars. This space is finite, but boundless. Astronomers face similar possibilities as they try to understand the real universe we live in, whose shape is still unknown. It is much larger than the simple spaces we've seen in the video and contains vast numbers of stars. But the same principle applies. What seems to be a star in a distant galaxy could be our own sun. The light we receive from it could be light which left the sun billions of years ago, traveled around the universe, and is just now completing its trip. If we can someday find a pattern in the arrangement of the galaxies, then we will know the true shape of space.
Hi, are you there? Sorry.
Yeah. How's it going?
Hi,
I'm back.
can you
Just
hear
one
me?
correction. I realized goes, real time,
Uh-huh.
then imaginary time, then reversed imaginary time, then reversed real time, and then around and
Oh,
around. Anyway, so that's the basic concept. I've no idea if that's right, but it seems more symmetric, and I think with possibly more research, we could find out whether it
yes.
makes sense or not. I mean, obviously, we're talking about something that's sort of impossible anyway, in a sense. Superluminal speeds. I know you work with superluminal, like the concept. So
Yeah.
obviously, we're open to it, but I mean, certainly within Ohm, within the Ohm model, we have instantaneous transmission of
Uh-huh.
information. But I think the point I'm trying to make with the with this whole thing is more the fundamental domains on the hypersphere, because if we look at a lot of the research done into thermodynamic gravity, entropic gravity, and that kind of thing, where we would have the bulk space and a hypersphere where everything is like the holographic projection concept, where everything is projected from a 2D boundary, and that boundary is like is a flat boundary. Obviously, it's a compacted thing. So that's very similar to what we'd be talking about. So like the projective point at infinity, like whatever's there is projected to infinity on the hyperplane. But you could compact that, and then when you then create all the fundamental domains that I was talking about on the sphere, those squares, you can make them infinitely small. Then that compacted boundary then stands for the line, for those lines, and then traveling through them would be akin to going around a Mobius strip, oddly enough, and it would take you going through two before you would come back to the normal kind of thing. And so at this point we have the normal time, real time axis, and an imaginary time axis. We might even be able to speak of like a negative time axis and a negative imaginary axis, which is fine, but let's just stick to those two. But then we have the concept that you could have, because there'd be two axes, you could have something like complex time, which would be a combination of the two somehow. And the interesting thing about complex numbers is that they're not ordered. So there's no way to go. You can't start from 1, 2, 3, 4 because they're complex. There's two things built together. So that would imply that complex time is not linear time. It has no order, which would basically be eternal, So there's certain states of mind that can be achieved either through meditation or hallucinogenic substances that flip the mind into a different mode of operation. So this could be like a different type of sense field in your concept. And then this different field then is not working in linear time or even imaginary time, but rather a combination of the two. And then the result of that is a kind of an infinite, because you could visit any moment in your life just by thinking about it, because there's no linearity to anything. Or the same moment could be, you could travel into the future and it could be the same moment that you left, in a sense, because they're all identical. There's no future per se, because no one moment preceded the the other moment. So when you arrive in the future, you're still in the exact same present moment you were before you left, because there's no concept of which direction time is moving or if it is even moving. And so in that realm, there's just an ever continuing present moment without any sense of movement. And that is essentially like infinity, kind of eternity. So where does that exist? Does that exist outside of the hypersphere? Is it in the realm of where those magnetic monopoles exist, with their instantaneous transmission of information? It's plausible, but we just don't know. We're applying certain mathematical things like the fundamental domain to reality, and I mean, it's logical that we can do that, but then you do have to break certain speed limits, cosmological speed limit to do it. So there's questions around that, but ultimately, I think the concept, if we're talking about more metaphysical things, yeah, complex time seems to, that's probably like when we talk about heaven and hell, that's like time stops there. So maybe it's a complex time situation.
So I just want to show I kind of sketched it. I don't know that you can see that. So I'm trying to see. So this is our real universe.
Oh, that's upside down, Raja.
Oh, it's upside down. Okay. Let me see. So I had to invert it. Let me check. Because I changed to solve the shadow problem, I kind of switched it around. Okay.
So, oh yeah, very good. The shadow problem is solved, but now everything's upside down.
Yeah, so I have to invert it somehow. I think there is a way to invert it. Let me check.
Kind of read a bit of that. So it says imaginary time, real time. And then I assume you're also talking about complex time there?
Yeah.
Okay.
So I may have to just, for now, I will do that.
Oh, look at that. Out later. Yeah, that's the way to do it.
That's a mirror. Let me see.
Sometimes the simplest ways are the best ways. Okay, so you got scalar real time and imaginary scalar time?
Yeah, so this is if I can write it upside down. So this is our, let's see. This is our scalar. This is our real universe. The scalar, the positive thing. This is our real observable universe.
Wait, are you saying that whole square is the observable universe?
Yeah, the whole square. That almost. But
does that make sense though? Because is our universe a combination of imaginary time and real time?
Yeah, that's an interesting thing. I mean, each universe has that. Probably every universe has that. But at any point in time, like we are measuring, right? Like we are experiencing the consciousness, the real universe. When everything is, what we see is what we get, type of thing. Then we are in this domain. But our mind can be here at times. Our mind can be here. Our mind can be here. So all the four quadrants. But when things are really happening, our instinct and what we are doing, we are moving, and we are experiencing the real aspect, then we are in this part where it's a scalar time. I say it's like 11:15 here going to be. So whatever your thing is. And then here the imaginary time, you are on this axis. where it is not complex. It's actually just real. But then we can move on, like you said, you can move on to this side, and that becomes complex. The boundary, if you want to
that's
call
not
it.
right though, because if we're in real time, at the moment,
Yeah,
and we're on the x-axis. We're not in that quadrant. If we were to travel,
positive x.
Yes,
positive x.
Exactly. If we were to travel at the speed of light, or beyond the speed of light, then we would arrive in imaginary time. So we would be at 90 degrees to real time, and then we'd be on the positive y-axis.
Oh, right.
Okay.
Okay.
Yes, and then any point in the place that you're calling of the observable universe would be a complex point between real time and imaginary time. So that whole space there has to be complex, and there's no way we live in. Well, I think you're right in a sense that we probably do live in complex time, but for whatever reason, we are like coupled to real time. So it just seems like time exists, but it actually doesn't. And
we are actually
all we
like
need to do is become uncoupled to real time for however we do that.
We are kind of connecting like that.
We always were living in complex time.
So like that, we kind of transcend between these two, kind of.
No, because both of those two are kind of the same. The other one would be complex, would also be complex time, but in that reality, the basis of it would be backwards real time. But it doesn't matter whether
here, one of these.
The minus x-axis is real time, but going in reverse. The minus y-axis is imaginary time in reverse.
Yeah, exactly. Yes.
Okay. So, but remember what we said about complex time is that it has no order. So it doesn't matter if you're in backwards real time, forwards imaginary time. When it's a complex number, it doesn't care about what's backwards and what's forwards. They're all there is no order. So all of the four quadrants there are identical. Now, one way that we could have the bottom half kind of removed is that oftentimes in mathematics, when we're dealing with modular forms and things of that kind, even the Riemann zeta function, I think, well, we often deal with the upper half plane, denoted as H, which
so it will be just like this.
The upper half plane. Yeah.
Like
so I think it's only where the imaginary axis is equal to plus I, but you could still have positive and negative real numbers. So yeah, so that's just a convention though. You could flip that around, but it is a way that a lot of the math is devised, and a lot of the models that particle physics uses that employ let's say SU2 matrices and modular forms and all of that, they would only be interested in the upper half plane. So
because symmetry, you can use symmetry.
It's not to say that the lower half plane doesn't also exist.
Because symmetric.
Yeah. So then, so possibly, if we were talking about complex time, you'd either be living only on the lower plane, meaning you're in hell, or on the upper plane, meaning you're not in hell, you're in heaven or something. So, but both.
You are just talking about this aspect. You're going this way.
You only want to be in the upper half plane. You don't want to be in the lower half plane. Both are infinite. There's no time in either of them. But ultimately, they're all the same thing. You should be able to move between the two. You just wouldn't want to. You probably wouldn't want to.
See, my rank 6 tensor will be a tensor like that, right? But then it moves into vector, and then it will point, like from here, it can point a vector to the scalar time here. So this will be a vector, and this will be a scalar, and this could be a tensor.
Okay, so write out a rank 6 tensor there is going to be what is in that?
So on this y-axis, it probably will be in the y-axis, the rank 6 tensor. And then it splits into the vector and the scalar like this.
I'm confused about rank 6 tensors. Would that not be a tensor with if you have a scalar is 1, a vector has 2 things.
So let me write in another place. So rank 6 tensor means it
would be a 6-dimensional tensor.
Yeah, it will have time. It's all time tensor. So you have alpha, beta, gamma. So you have 1, 1, 1, 1, something like, and t 1, 1, 2 or something like that. So like that, it keeps going. Each one is
yeah, but that's only 4.
Right.
So in a rank 6 tensor, it would have 6 indices.
6 of them, yeah, 6. So you have 4, 5, 6.
No.
So they are all vectors.
Oh, yeah, that's right. Yeah, 6. But then
they'll all be vectors.
That would be 6. No, that's wrong, Rajan, isn't it? Oh well, maybe not.
No. Yeah, the vectors. 1, you have 1, 2, 3.
No, I think that
4,
that is wrong, Rajan. It's not that you would have 6. It could be any number. It could be like an infinite number, but the fact is that you have 6 dimensions. So let's say in a cube.
Oh, you are talking different. Yeah.
No, but this is actually how it is, because I was making this mistake before. In a cube, it has 3 dimensions. Yeah, length, width, and breadth. Now, let's say that cube had. Well, let's go back to a rank 2 tensor. Yeah. So we're just dealing with a matrix like you have there. What you've actually drawn is a rank 2 tensor. So yes, if we go back to a rank 2 tensor, and let's say we put 3 items in it. So we have 1, 2. So you've got 2. Okay, so that's a rank 2 tensor. But if you put 3 items in it, put a third one in. So it's 3 by 3.
Here?
No, 3 by 3.
Oh, okay.
Yeah. Okay. That's yeah. That's
one more.
Yeah, one more, exactly. That's still a rank 2 tensor, yeah?
Yeah.
Okay, so
yeah.
Because it's 2-dimensional. But if you were to add a third dimension to that, so now we have so there's 9 there, but if you were to make it 27, that would now be a rank 3 tensor, I'm thinking. And so if you had a rank 4 tensor, it would be a 4-dimensional tensor, like the hypercube. And then rank 6 would be a 6-dimensional cube, essentially. That's what the matrix would look like.
And there will be 6, I was showing that. So you have, like here, they'll have 6 like that, all of it.
I don't think so. Is that how they write it?
I think so.
You think so?
They'll be. Yeah, but tensor means it. Yeah, I had to figure out. But this is the way they are written it, but you can transform it. You can actually change it.
But in reality, they wouldn't do that. They would just write the letter G, let's say, or T, and then they would have a subscript of 6 indices.
Yeah, it's a different.
Because what you've done there is you've just created a rank 2
It's not the same. It's not the same. It's not same thing. I mean, each one is different. Like one. All of them should be different. I just wrote it.
That wouldn't matter though. That wouldn't matter, Rajan, because if I wrote, let's say I wrote G as the tensor, and then I have a subscript A, B, C, D, E, F, which is 6, then each of those A, B, C, Ds, that's all of them. And if you were to calculate the number of that, that would be 6. Is that 6 factorial or what?
Yeah, we have to figure out. I think it has 36 elements, something like that. More than that. No, sorry. There's a lot
more
of
than that.
elements. Yeah. 6 factorial will be, let me calculate. 6 factorial will be 6 times 5 times 4 times 3 times 2. So
720.
30 times 2.
720.
3, yeah. So it is, yes. Yeah, 720. It'll be 720. Yes.
Are we sure, though, that that's the right thing to do, to apply factor? I think it is.
Yeah. Yeah, it's 720 elements to that.
Well, is it though? Because yeah, if I have 3 dimensions and I have 3 indices. Well, let's look at a rank 4 tensor. That's still not a very good idea, probably. But some of them will be duplicates as well.
Yeah. So it's a permutation. It's a 720 permutation. But actually combination.
But you don't have 720 there. At most you have 36.
Yeah. I know that's because each one has its own submatrices. You see that? It'll point to another matrix. Point to another.
Yeah, but why not just, if you want to do it shorthand, why not just go like G with a subscript of A, B, C, D, E, F, G, E, F?
Yeah, we can do that. Yeah.
But also, I don't think it's correct. I don't think that would be correct if you have like a matrix with 6 in it, and then each one has a submatrix of like 2 or whatever. That wouldn't be a rank 6 matrix then, would it?
Yeah, it will still be rank 6, but it has submatrix.
No, it'd be a rank 2 matrix with rank 2 matrices as elements in that matrix. So I don't know what that would be. Is there a rank for that? Would that be a rank 2, maybe?
Yeah, the actual elements, for example, you have this factorial coming in, right? The factorial may be because of this one, because it is submatrix. So the factorial will take into account that. So you get 720 because of this.
No, you wouldn't. I don't think so. Let me think. If you have a rank 2 matrix with 6 elements in it, then that is, it would just be rank 2. And then
2 will have only 2 times 1.
In that case, I don't think it would be factorial necessarily, but it would be 36 elements. So each of your you would have, if you were to write that, then you'd have like G the subscript would be just A, B, yeah. And each of those, like so A, for instance, can go from 1 to 6, and B can go from 1 to 6. So then you go 6 times 6 equals 36. Okay. So similarly, A will go from 1 to 6 because you have 6 along the x-axis. And B would run from 1 to 6 because you'd have 6 along the y-axis. And so that's 6 times 6 equals 36.
So you have G1, 1, G2, 1, G3, 1, G4, 1.
So to get the size of the rank 6 tensor that we were talking about, there's assuming it has 6 things in it, and that would be 6 to the power of 6, wouldn't it? Which would be
So you are saying something like that and keeps going
46,656.
like that. You are doing something like this, right?
Yeah, that's right. But so you see what I mean? So that's a rank 2 tensor because it only has 2 indices at the bottom. GAB, yeah.
Oh, yeah.
But A can run from 1 to 6, and B can run from 1 to 6. So that's 6 times 6 equals 36. But if you had an actual, if you had a 6-dimensional tensor, then with that ran from 1 to 6 in each dimension, that would be 6 times 6 times 6 times 6 times 6 times 6, which is 6 to the power of 6, which means that it has 46,656.
Wow.
Yeah, it's big.
Yeah.
And that's arbitrary though, because it's a dimensionally 6. Its dimension is 6, but its size could be infinite. You know, so when we say 1 to 6, that's arbitrary. It could be 1 to 8. It could be 1 to infinity, which means it would be an infinite sized 6-dimensional matrix or tensor. Sorry. And as we know, when we use tensors, they're usually trying to express some smooth or continuous surface, and therefore they should be able to account for infinite degrees.
Smooth manifold. Yeah. See, that's why umbrella may be good because
like an infinite number of values, not running from just 1 to 6, but 1 to infinity, maybe. But I don't know. Like I say, I'm no expert in that field.
I will look into that more. I'm looking into that more, but I will only initially use fundamental things because the actual physics, just to develop the math, but I want to develop the physics. And I think umbrella is the best one. So far, I said umbrella model is the best one because you have to define a smooth manifold. Umbrella will be a smooth manifold. But then what happens if that manifold get ripped? Like umbrella get ripped. These are the things, interesting things that can happen. So ripping out the space-time and all that, the smooth manifold become fractal or fractured. Things like that. So that's interesting aspect of that. But one step at a time. So I want to develop enough math, just enough to get to the physics, because I don't believe we should go too much into detail of math, because the math people can take on from there. But to the level that we can apply physics and understand what's going on. So that's what I'm trying to do. And then of course I'm going to go into what you said. I mean, that's true. Because in my OJPS also I mentioned about alpha, beta, gamma, the tensor, but that tensor is like rank 4, maybe rank 2, 4, maybe. But when I find that you need up to rank 6 tensor somehow with the group theory and everything, it's necessary to have rank 6 tensor. But then I had to figure out, I'm calling it rank n tensor. What at n is what you have to figure out. I think it's going to be 6, but what happens then? If it's rank 6 tensor, does it describe the 6 dimensions we are talking about? Then
well, it would, yeah, because it would be a rank 6 tensor, so it would have 6 dimensions.
Yeah. So then you have 6 universes with each of them having this rank 6 with the tensor, as well as the 4 dimensions. So each one will have the 24 thing, 6 times 4. So each of the universe will have 24 with the space and time. And then so you have 6 universes like that. So what are those universes? One of them could be mirror universe, another could be inverse universe, but they could be that counts about 4 of them, I think.
I think the mirror is inverse, isn't it?
Not necessarily. It's not. Mirror and inverse are not the same. See, mirror is a reflection, right? Yeah. Whereas inverse is you're inverting the whole thing. So mirror is like if you are rotating, mirror is like you are on one side, you are on the 180 side, 180, right?
Yeah, it flips horizontally, doesn't it?
See, if you look at a mirror, it only what is near becomes they become near on the other side. What is far, they become far apart, far apart. That's what a mirror is.
I think
And
Feynman mentioned something about a mirror flips horizontally.
I had done, yeah, I had to look into. I had done this some time ago because
what we have
that's
to
very
understand
important.
though is that if you have a spaceship that's traveling at the speed of light, let's say, and it's contracting. Now, I think they usually say that it contracts along the direction of travel, but I'm not sure I'd agree with that. I would say that it probably contracts in every direction equally. And then once it gets to the point where it's no longer, where it's completely flat, like, then when it's kind of, it starts expanding again, we could, if it's going into a mirror universe, it's like expanding through itself. So one way of thinking about that is to go back to, I'll share the screen again. Entire screen. Share. If I go back here, and we go to -1, yeah, which is an inverse. So here's the spaceship. Here's the front of the spaceship, the back, the left, and the right. The front gets flipped with the back, the left gets flipped to the right, and this side gets flipped with that side. That side gets flipped with this side. So that's what I mean by mirror or inverse.
Actually, mirror is not like that. Mirror is a planar, right? You are like your mirror in the middle.
I know, but I'm thinking that we're talking about a mirror thing is a 2D thing usually. Because we're looking at a 2D surface. But this will be a full 3D transformation of an object that's in 3D. And the result of that won't be a normal just flipping around one axis. I believe it'll flip all the axes.
But that's not mirror. Could be inverse. Mirror
yeah,
inverse
it is inverse. Because -1 is inverse to 1. But we're just calling it a mirror universe because mirror universe is...
I think mirror is a specific form of inverse. Inverse is more general, I think.
I know, but well, mirror, the term mirror universe, though, is not, I don't think it's a scientific term. It's like probably from science fiction or something. So, okay, to be more accurate then, we'll probably say that it's an inverse universe.
So there are two inverse universes. One is positive inverse, the other one is negative inverse, probably.
Well, there can only be negative inverse, can't there? Because there's our universe, which is 1. Then there's the inverse, which is negative. So the inverse to our universe.
Inverse is not only negative. See,
this
inverse
one
is not
though, look, because
negative.
when we apply -1 to our universe, we get the inverse. And then we have the inverse space with negative time. We have the inverse space with positive time. And we have the real space, the normal space with positive time and the normal space with negative time.
But when we say inverse, they are in terms of operations, they're additive inverse and multiplicative inverse. You know what I mean? Additive inverse is positive and negative.
0 is the multiplicative inverse, isn't it? Or no, that's the identity.
Of infinity. 0 is the multiplicative inverse of infinity. 1 over infinity is 0.
Hang on, what is the inverse? Multiplicative inverse?
1 over. If x is the thing, then the inverse is 1 over x.
Oh yeah, so
that's what multiplication.
What is that? Is that equivalent to like x to the power of -1 or something?
Yes, x to the power -1.
Okay, so what am I thinking of then?
0 but additive is a positive x, negative x is additive.
0 is the additive identity. 1 is the multiplicative identity.
Yes.
Multiplicative identity. Okay,
Exactly.
and so yeah, so I was getting mixed up between the identity and the inverse there.
Okay.
True. -1 is the. Okay, well, okay, so you're talking about you're moving into a different field though, because there's a difference between like 3 and then its inverse being a third, and what we're talking about, which is
3 is negative, 3 is additive inverse. 3
well,
and
no, but
negative
you're
3
getting
are
far
additive.
you're getting far too into the maths. We're more interested in the geometry. Look at the
Yeah, it's the same thing applies. Same thing applies.
I don't think so, because look at this box here with the 3 or the 9 dots in it, yeah? The front of the spaceship, the back of the spaceship, the left and the right, and they all get flipped around. Now, if you're going to apply a kind of an inverse that takes these 9 dots and inverts them in a mathematical way so that we now only have 1/9, then that's going to be just one of these dots, which is which could be any one of them. It could be the front of the ship. It could be the back of the ship. But it doesn't mean anything, because then we've just said we destroyed our ship. We only have 1/9 of it left, and we don't know which part that is. It's interesting, but it just doesn't fit into anything.
Inverse topology, maybe. Inverse topology.
Yes, that's what this would be, because it's a shape and it's being inverted topologically.
Okay, inverse topology. That makes sense. I think.
Yeah, a bit like this actually, Rajan, with the something I didn't get to with the toruses and the Clifford torus. See this. If I where did it go? That's not right. Should be widgets associated with this. Maybe I have to change them by hand for some reason. But if I change this value from that to 0, we get a torus, yeah? And then if we continue to rotate this in 4 dimensions, it will turn into what you saw before, and then it'll start to expand outwards, and then it will invert. It will go completely inside out. So, for instance, I could look up Clifford torus. Oh, I spelled that wrong. This, see, it expands from 4D, and then it's now inside out. See what I mean?
Okay.
The inside is now the outside. So I'm just going to close that again. Yeah. So we can. So that's another thing I was looking into, which was this problem. And what I wanted to do was wrap a toroidal knot around the donut, and then expand it using a 4-dimensional projection, stereographic projection, into a 3-dimensional elliptic curve, which is this. So if I zoom in here, kind of in there, you see the way there's like the sort of the whole of the torus is now tiny, and it's this circle here. So what I've been trying to do is I need to find out what the dimensions of that circle is there. So what I need to do is get this equation that does all of this. It does all of this, and express it in terms of y, or where y, or express it where y is equal to 0. So I attempted to do that. If I change this to true, by just setting all the values to 0, except for setting all the values of y to 0, and then mapping it again, and I get this. So this looks like it might be the circle that we want, but I can't tell if this is an ellipse or not, because there's a chance that this could be slightly elliptical.
Yes.
But the idea is, okay, so if we go back, we change this to false. From a string theory point of view, the circumference of this ellipse or circle will give us the mass of an electron, let's say. But if we go back here, when we zoom in here, so that that would be see the way we have these kind of this dumbbell shape going on.
Yeah.
And then in the center of the dumbbell shape, there's, if you look, there's a circle behind the numbers, and that wraps around one of the tube of the torus. Now, if you were to get that exactly bang in the middle, so that I guess z equals 0, or it should be y equals 0. But anyway, if you were to get that bang in the middle, then you get the circle we saw earlier, or possibly an ellipse. But if you were to if you go out either direction, that circle is going to get bigger, which means the circumference gets bigger, which means the mass also gets bigger, which means that we could say, oh, you need to rotate the circle by whatever 0.001 pi to get the mass of, you know, the tau electron, or the top quark or the bottom quark, or whatever it is that you're looking for. So that could be a good thing. It would also imply that all the particles are just one particle, and that they're just offset on this torus or 3D elliptic curve by some amount, which would be interesting. And like maybe that offset might be something to do with the speed that it's traveling at, you know, with respect to this space. So it has momentum because of its speed, which means that it's all the one particle, but it just has different mass.
Field. Suppose we take a content in terms of the field, the content. If we say a particle is a condensed field, right? And the way we expanded field, then I think that would make sense. So when it condenses, it becomes particle at some point, and then expands, it becomes wave, and that becomes imaginary. So the field can be, of course, we need a gauge field. You know, the field is not conserved. Maybe the gauge field is conserved, you know, because the differential of that is conserved. Of course, we know the Planck, the energy time is conserved because of the Planck constant. So the time does make sense, energy. And like that, thermodynamics says conservation of energy, then we need conservation of time. And that will make sense because Planck says that energy times time is conserved. So I think that will make sense. So I think, yeah, we can put together all this. I think it's possible. And then think in terms of condensed field, expanded field. Like particle is just a condensed field, and wave is an expanded field. So then I think all your transformations automatically become smoother. So then in different part, how it becomes, you know, different shape, dumbbell shape or anything, I think we can probably be able to do that. But what is conserved, the conservation itself may be the gauge field. So we have to, you know.
Oh yeah,
that's a gauge.
That's interesting. Yeah, because I mean, I think your thinking is very much along the lines of my thinking. So I haven't been able to get this completely right yet, but imagine this looped torus knot is sitting on the torus, not outside of it. I mean, I can get it so it sits inside, but right. So let's say it was there. This torus knot then represents what we saw earlier, the harmonic oscillator of the particle. And then if we have this perfect with the torus knot on the torus, and then we convert it into this, what we're going to have is the harmonic oscillator will wrap around this part, and then it will expand out to infinity around the rest of it. So that could be like what you're talking about, where you have particle here and field, infinite field out on the other side. That could be another interesting thing. It'd be really good to sort that out. But even if we get to the point, you know, where we put this torus knot on the torus, we still have the problem of how to turn it into this, you know, how to wrap it around this structure. So that's kind of my thinking with this presentation. Was less that I wasn't really supposed to talk about my ideas for the whole of the time. We were supposed to get into a point where I would code the work, and maybe you'd work on a section like converting the equation into what you call it, like an implicit form, and then express it as y, so that we could, you know, while I was working on some other element or something. So next time, I don't think we're going to do it next week. We have a different agenda.
Next week, we probably we can kind of edit our videos, something we are talking about.
We have a different agenda. That probably won't take a day, though.
The one after that, the 4th of May or something. The week after.
Maybe, but
and then 11, I will do episode 3, 11.
Great. So one of the days we'll do another thing. So the idea is, I might send you on the code then ahead of time, so that you can maybe work, you know, you can work on it in your spare time or whatever, and then during the thing, obviously, and then we can combine what we've got, either during the thing or ahead of time, and then that's pretty good. So that's a plan. Okay, so we might as well leave it there, because we've 2.5 hours. Pretty good.
Yeah, that's good. Yeah. Okay, thanks a lot, and then we'll work on that.